Hello, dear students. Glad to meet you again in this session. In this session 2.2, we are going to discuss about the atomic models from chapter 2, Structure of Atom in grade 11. Before getting into this session, let us recall what we have discussed in the previous session. In the previous session 2.1, we have discussed the subatomic particles and the discovery of the subatomic particles like electrons, protons, and neutrons. And we have discussed the properties of the fundamental particles, that is the subatomic particles of an atom, electron, proton, and neutron. Learning outcomes. Students, at the end of this session, you will be able to describe J.J.Thomson Atom model, describe discovery of X-ray, define radioactive elements, list the kinds of radioactive rays, explain Rutherford Atom model and his drawbacks, recall atomic and mass number, and define isotopes and isobars. From various experiments that we have discussed in the previous session, we come to know that Dalton's indivisible atom is composed of subatomic particles. J.J.Thomson's atom model resembles the inner part of the watermelon. J.J.Thomson in 1898 was the first to propose that atom possesses a spherical shape of uniformly distributed positive charge of radius, which is approximately equal to 10 to the power of minus 10 meters, in which electrons are embedded. He also suggested that mass of the atom is evenly spread over the entire atom, and it could explain the neutrality of the atom. Though it could explain the neutrality of the atom, it could not explain certain observations by Rutherford in his alpha particle experiment, which we are going to discuss in the later part of this session. J.J.Thomson's atom model is known as raisin pudding model or watermelon model because of the similarity between these two. Though J.J.Thomson was the first to propose the structure of the atom and it explains the neutrality of the atom, his model has some drawbacks. Drawbacks of J.J.Thomson atom model. His atom model could not explain the stability of atom, and it could not explain how the positively charged protons and negatively charged electrons are arranged in an atom, and it failed to account for the position of nucleus in an atom and failed to explain the scattering of alpha particle bombardments on atom. Before discuss about Rutherford alpha particle experiment, let us discuss about X-ray and radioactive rays to understand more about alpha particle radiation. In the later half of the 19th century, different kinds of rays were discovered. While Wilhelm performed experiment with cathode rays applying high voltage, he was amazed to note some unknown rays produce fluorescent in the fluorescent screen when electrodes strike the material in the cathode ray tube. Then he wrapped that cathode ray tube with a black sheet and applied high voltage in the cathode tube. These unknown rays could produce fluorescent light in the fluorescent screen made up of zinc sulfide, which is placed outside the cathode ray tube. Since Wilhelm Röntgen did not know the nature of the radiation, he named them as X-rays, and the name is still carried on. So X-ray was discovered by Wilhelm Röntgen in 1895. Coolidge tube is a modified tube of Crookes tube discovered by William Coolidge in 1913. It works with a very good quality of vacuum, about 10 to the power of minus 6 mm pressure. Now let us see how this apparatus works to produce X-ray. In this apparatus, tungsten filament is taken as a cathode, which is kept inside this molybdenum cylinder. They have taken tungsten because tungsten can withstand high pressure up to 2700 degrees centigrade. Here the molybdenum cylinder is connected to the negative terminal to maintain the negative potential, because this negative potential helps the electrons produced in the tungsten filament, which is inside this cylinder, and helps the electron to direct towards the molybdenum anode target without any deviation. Here the same molybdenum metal is taken as an anode and it is embedded in a copper block. This copper block helps to conduct the heat which can be cooled by this water system. Electrons are produced by passing high potential through the tungsten filament which is kept inside this molybdenum cylinder. Here in this picture 1, you could see the cathode tungsten filament inside the molybdenum cylinder. I have zoomed picture 1 to see inside the molybdenum cylinder. Here inside this molybdenum cylinder, you could see the cathode tungsten filament. These green dots represents the flow of electrons from this cathode tungsten filament. I have zoomed the anode part of this apparatus in picture 2. In picture 2, you could see the anode part of this apparatus. Anode is kept at 45 degrees so that the X-rays produced can fall perpendicular in the downward direction. Here in picture 3, you could see the X-rays that produce fall perpendicular in the downward direction. When highly accelerated electrons strike the molybdenum anode target, the electrons slow down, and as a result of that, these electrons radiates its energy in the form of rays called X-rays. Application of X-ray. X-ray is widely used in the field of medical science. It is used to detect or diagnose bone fracture. Radioactive elements. The discovery of subatomic particles like electrons, protons, and neutrons was further supported by the discovery of radioactivity of certain elements. Henry Becquerel in 1896 observed certain elements emit radiation of their own. These kinds of elements are called radioactive elements. The rays from these radioactive elements are called Becquerel rays. Henry Becquerel found that all salts of uranium and metals like thorium emitted powerful radiation. These radiations are invisible to the naked eye and has the power of ionizing gases. Moreover, this property is independent of temperature and other physical condition, whether it is in the elementary state or in the combined state. Radioactivity is defined as the spontaneous emission of active radiation by certain metals like uranium, thorium, and radium. This field was developed by Marie Curie, Pierre Curie, Rutherford, and Frederick Soddy. When a radioactive source like uranium mineral is kept in a lead cavity and allowed to emit rays, and when magnetic field is applied, the radiation was resolved into 3 directions. The rays bending away from the magnet were called alpha rays. The rays bending towards the magnet were called beta rays. The rays not deflected by magnetic field were called gamma rays. Radioactive elements under electric field. Instead of applying magnetic field, when electric field is applied, the radiation was resolved into 3 directions. When electric field is applied, alpha rays deflected towards the negative plate and beta rays deflected towards the positive plate, and gamma rays do not deflect because they don't have any charge. When you look at the penetrating powers of alpha, beta, and gamma rays, beta particles are 100 times larger than that of alpha particles. So it can penetrate through paper. And when you come to gamma particles are 1,000 times larger than that of alpha particles. So it can penetrate through paper as well as through thin sheet of wood or aluminium. Characteristics of 3 kinds of radioactive rays, that is alpha rays, beta rays, and gamma rays, are given in this table. Rutherford found that alpha particles consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass. Rutherford concluded that alpha particles are helium nuclei, and when alpha particles combine with 2 electrons, it will yield helium gas. Beta rays are negatively charged particles similar to that of electrons. Gamma particles are high energy radiations like X-rays. They are neutral in nature and do not consist of particles. The velocity of alpha rays is nearly 1/10 as that of light, and the velocity of beta rays is nearly same as that of light, that is 3.0 into 10 to the power of 8 meter per second, and the velocity of gamma rays is same as that of light. Rutherford scattering experiment. In 1911, Rutherford carried out an experiment for testing Thomson's model. In his experiment, bombardment of a thin sheet of gold of thickness 100 nanometer was carried out by alpha particles. Such a thin gold foil contains approximately 1000 atoms. Lesser the atom, more convenient the experiment will be. He selected alpha particles because they have high energy and heavier at the same time. Heavier alpha particles can pass through the light pudding structure of the atom in the gold foil. These alpha particles was obtained in the form of a narrow beam through a slit in the lead block. A circular fluorescent screen coated with zinc sulfide is kept around the gold foil to detect the deflections of the alpha particle. Whenever alpha particles strike the screen with zinc sulfide, a tiny flash of light will glow at that point. Rutherford, to his surprise, observed that most of the alpha particles pass through the gold foil in a straight lines. Some of the alpha particles were deflected by small angles. A very few alpha particles were deflected either by small angle or turned back on their path. Rutherford explains his observation as follows. Since most of the alpha particles pass through the foil undeflected, it indicates that most of the space in an atom is empty. Alpha particle being positively charged and considerable mass could be deflected by some heavy positive charge center. The small deflection of alpha particles indicates the presence of heavy positive center in the atom. Rutherford named this positive center as nucleus. Alpha particles which made head-on collision with the heavy positive center are deflected through large angles. Since the number of such alpha particles is very small, the space occupied by the heavy positive charge must be very small. Bouncing back of few alpha particles indicates that the nucleus is rigid. On the basis of alpha particle scattering experiment, Rutherford proposed nuclear model of atom. The nuclear model of atom has the following significant points. Most of the mass and all the positive charge of an atom is concentrated on nucleus. The positive charge on the nucleus is due to the presence of protons, and the charge on the nucleus is different for atoms of different elements. Nucleus of the atom is surrounded by electrons, which is moving with a very high speed in a circular path called orbit. Most of the space inside an atom is empty. Atoms are electrically neutral since the total negative charge on the electron is equal to the total positive charge on the nucleus. So, atoms are electrically neutral. Electrons and nucleus in an atom are held together by the electrostatic force of attraction. The electrostatic force of attraction between electrons and the nucleus is balanced by the centrifugal force acting on the revolving electron. Since all the positive charge of the atom is concentrated in a very small region called nucleus, the size of the nucleus is extremely small when compared to the size of the atom. The radius of the nucleus is in the order of 10 to the power of minus 15, whereas the radius of the atom is in the order of 10 to the power of minus 10 meters. For example, if we consider the size of a cricket ball represents the size of the nucleus, then the radius of the atom would be about 5 kilometers. Nuclear model of atom can be compared with the solar system.
In an atom, the electrons revolve around the nucleus is just as the same way as the planet revolve around the sun. Due to this comparison, the revolving electrons are sometimes called as planetary electrons, and Rutherford nuclear atomic model is also known as planetary model of atom.
Drawbacks of Rutherford atom model. Rutherford atom model failed in the view of electromagnetic theory given by Maxwell. According to Maxwell's electromagnetic theory, a charged particles when accelerated emits radiation in the form of electromagnetic radiation. In Rutherford atom model, electrons are revolving around the nucleus. Electrons are in the state of acceleration at all the time. So they show continuous emission of radiation. Because of that, they would slow down and no longer be able to withstand the attractive force of the nucleus. It would move closer and closer to the nucleus and follow a spiral path and collapse in the nucleus. This means atom should collapse. Rutherford therefore could not explain the stability of the atoms. Not only that, it does not explain the distribution of electrons around the nucleus, and it does not explain anything about the energy level of the electrons. He failed to explain the existence of certain definite lines in the hydrogen spectrum, which we will discuss in the later session of this chapter. Atomic number. In 1913, Henry Moseley calculated the charge on the nucleus from the frequency of the X-rays emitted by different elements. The number of unit positive charge on the nucleus of an atom of the element is called the atomic number of the element. Since positive charge on the nucleus is due to the presence of proton in the nucleus, and each proton carries 1 unit positive charge, therefore the atomic mass of an element is equal to the number of protons in the nucleus. The atomic number is denoted by the letter Z. Since number of protons is equal to number of electrons in an atom, we can also write atomic number Z is equal to number of electrons in a neutral atom. Mass number. The mass of an atom is mainly concentrated in the nucleus. We know that mass of an atom is mainly due to protons and neutrons present in an atom. Protons and neutrons collectively called nucleons. The capital A mass number is equal to number of protons Z, that is the atomic number, right? Plus number of neutrons, which is represented by small n. So we can also write mass number A is equal to number of nucleons. Representation of atomic number and mass number. Mass number A and atomic number Z of an element are generally indicated as follows. If the position of the letter X represents the symbol of the element, then to the top left corner of the symbol of the element, we can write the mass number, and bottom left corner of the symbol of the element, we can write the atomic number. To understand better about the calculation of atomic number and mass number, let us do the following calculation. Calculate the number of protons, neutrons on electrons in bromine having mass number 80 and atomic number 35. Solution. Mass number A equal to 80 and atomic number Z is equal to 35. Since it is a neutral atom, the number of protons will be equal to number of electrons. We know that the atomic number is 35. So, number of protons present in this element is 35 and number of electrons present in this element is also 35. Now let us calculate the number of neutrons. Mass number is equal to number of protons and number of neutrons. So from this expression, we can calculate the number of neutrons. So to find the number of neutrons, we have to deduce the number of protons from mass number. The mass number A equal to 80 and the number of protons, that is the atomic number Z equal to 35. So 80 minus 35 gives 45, which is the number of neutrons present in this element. Now let us discuss one more example sum to calculate the atomic number and mass number. Here they have given the number of electrons, protons and neutrons in a species are equal to 18. That is the number of electron. 16, that is the number of proton, and 16, that is the number of neutron respectively. Assign the proper symbol to the species. Solution. Number of electrons, how many number of electrons they have given? 18, which is not equal to number of protons that we have to note down. Since atomic number Z is equal to number of protons, Z is equal to 16. If the atomic number is 16, then the species is sulfur. Here we have excess number of electrons. How many excess number of electrons we have? We have 2 excess number of electrons for sulfur. Now let us calculate the mass number. Mass number A equal to number of neutrons plus number of protons. How many number of neutrons they have given? 16. How many number of protons they have given? 16. So 16 plus 16 gives 32. So the mass number is 32. So the species is sulfur here. So the symbol is S and the atomic number is 16. So we have written 16 at the bottom corner and the mass number is 32. So we have written the mass number at the top corner in the left side of the symbol of the element. And here in the right top corner, we have to write the charge, that is -2. So the species is nothing but sulfate ion. Isotopes. All the atoms of a particular element have same number of protons in their nuclei. However, the number of neutrons may be different. The atoms of the element with the same atomic number Z but have different mass number is known as isotopes. For example, hydrogen has 3 isotopes. They are protium, deuterium and tritium. All the 3 isotopes have same atomic number, that is 1. Here 1 proton, here also 1 proton we have, and here also 1 proton. However, their mass number are different. Mass number for protium is 1, deuterium is 2, and the mass number of tritium is 3. Here we have isotopes of carbon. Here also we have 3 kinds of isotopes. They are carbon 12, carbon 13 and carbon 14. All the 3 isotopes of carbon have 6 protons, but they differ in their number of neutrons. The isotopes of other elements do not have special name. They are indicated by giving the mass number value on the symbol. Isobars. The atoms of different elements which have same mass number is called isobars. For example, we have taken argon, potassium and calcium. Here all these elements have the same mass number 40, but they have different atomic number. So these are called isobars. Chemical characteristics of an element depends only upon the atomic number, not mass number. Students, let's recall all the topics that we have discussed in this session. In this session, we have discussed J.J.Thomson Atom model, discovery of X-ray, and we have discussed the radioactive elements and 3 kinds of radioactive rays. We have discussed Rutherford Atom model and its drawbacks. We have discussed atomic and mass number and its calculation, and we have discussed the definition of isotopes and isobars. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.